Hi, welcome back. We're still at the home edition of my lecture videos. This one is going to cover arc length. Now, we had just done one previously looking at arc measure. I want to take a moment to those. Again, this will be helping you out on the practice sheet 10 to measuring angles and arcs. You'll see the walkthrough of that show up in just in the next video or so. Review what we talked about in the previous video because it leads us directly into arc length. The previous video was about arc measure, and we talked about this important concept right here. The fact that the arc measure is measured in degrees, just like angles. In fact, we get the angle measure of an arc off of the central angle that's creating it. We'll find later on as we move into some special arcs that there's different relationships when we've got different types of chords and inscribed angles that are creating these arcs. Right now we're going to start with the most simple case, and that is when the arc is being created by some sort of central angle. Again, here, according to the arc measure, when the arc is created by a central angle, the arc measure in degrees is going to be exactly the same measure as the central angle in degrees. Whoops, I dropped my pen. But this time we're going to be looking at the length of an arc, the actual physical distance that if you were, say, an ant on a sphere, or I guess a person walking around on the surface of the earth, if we assumed that the earth was completely flat, we would trace out the actual distance that we'd go from one together along an arc. So we're going to take a moment to remind ourselves of the definition of arc length. The arc length definition, according to our cue cards here that you guys were working on over the weekend, is that the fractional distance of the circumference of a circle is defined by the arc. All right, so let's sketch out circle real quick. Again, just freehand a circle. It doesn't have to be perfect or beautiful. Clearly mine is having issues this morning. Hello. All right, so here we go. Let's have a circle C. Okay, so in circle C, with some arc T to A. Okay, so here's our arc right here. So we had the measure of the arc being the measure of whatever the central angle was, but I no longer care about how far I have to rotate to sweep across the outside of the circle in order to trace out this arc. I really want to know physically how far would I have to go if this were the surface of the earth and I was walking from point, I don't know, T, Texas to some point A, Alabama. I don't know, I'm just making stuff up. But if I had to walk this distance along the surface of the earth, how far would I physically have to walk? I'd rather take an airplane, but that's... So our definition, let me pull it back up again. Our definition says that it's the fractional distance of the circumference as defined by the arc of the circle. So if I call this distance that I have to walk, this symbol alpha that we found when we were doing definition of arc length, then we need to know a couple things. And here's that formula that we saw. The arc length alpha is to the circumference of the circle, 2 pi r. Remember that r is the radius, so it's this distance here in the center of the circle and one endpoint of the arc. So the arc length alpha is to the circumference of the circle, the same way that the measure of that central angle, theta, so this angle right in here, is to one full rotation of the circle 360 degrees. Let's go ahead and play with this formula now and put in some numbers. So let's say we want to find this distance here. We need to know a couple of things. The first thing is we need to know the radius of the Earth. I think, you know what, I'm going to do a quick Google search and figure out what the radius of the Earth is so that we can this example going of Earth is, according to Google, 3,959 miles. So there's our circumference, and now we need to know what angle measure from the center of the Earth we would need to sweep in order to trace out this path going from the starting point, Texas, to the ending point, Alabama. And let's just make up a number here. Let's say that that's 12 degrees of an arc measure, this angular sweep that we're doing starting from the center of the Earth. So I'm just going to fill in what we know. So I'm looking for alpha arc length. I have now the radius of the Earth. Thank you, Google search. I know the angle that we have to sweep in order to cover that distance. And now I can solve this proportion for alpha. I'm going to turn everything into numbers and then do my cross multiplication because this is starting to really get to me. So 2 times 3,959 is 7,918 according to my 4-function calculator. And I'm whoops. Hello. I wrote that in the wrong spot. Sorry. Alpha over 7,918. I'm going to keep the pi for now, assuming that we want exact distance. We'll get into the approximate distance, which will make a little more sense in terms of context of how many miles you actually have to walk to go from, I don't know, Texas to Alabama. All right, I've got my proportion this way. Everything is numbers. I know that looks like a funny symbol. It is, but remember that it represents a number, so this denominator literally is just this number times this number, some other number, but I'm going to leave it this way for now. I'm trying to solve for this arc length here. 2 ways I can go about it. Remember, this is a proportion. 1 fraction equals fraction. Whenever you have this set up, you can cross multiply. Or I can look at this right here and notice that my arc length is being divided by some number. And there's no other variables anywhere else in my equation. And so if I just multiply through everything by this value down here in the denominator, it'll clear it out on the left hand. So that's what I'm going to do. That's going to save me just a few steps, a little bit of work. So here I am writing that I've multiplied everything in the equation through by that 7,908 pi, which clears it out on the left-hand side. I'm left with just alpha, arc length of that arc, equals this whole big mess. So I'm going to go ahead and find the exact value. I'm going to do that by doing this division right here. And I can do that, and it's going to give me, oh, that gives me the fraction. Here we go. Since I want to try to keep it in the exact values for now, I'm going to bring this up into the numerator. So 12 times 7,900 I may have to do some reducing here to keep it exact. Let me go ahead and reduce now, I guess. Both things are divisible by 12. So 360 divided by 12. This 12 is going to cancel, and it's going to leave 30 down here. Both of these numbers are even numbers, which means they're divisible. So I'm going to divide this top number here by 2. And the bottom number divided by 2, 30. Oh, excuse me. 30 divided by 2 is not 30. 30 divided by 2 is 15. All right, and I'm going to stop there because I don't know if that top number is divisible by 3. And yes, I have a 4-function calculator that out for me. But when I put that in, it spits out decimals. So this would be the exact distance, alpha, if I had to walk along the surface of the Earth 12-degree arc measure. But if I were trying to actually figure out like how far I would have to walk, I can't say, hi, I'm going to walk 3,959 pi. That's not how we talk. So we're going to go ahead and simplify this out. I'm going to take that 3,959. I'm going to multiply it by some approximate value for pi. And then once I have a number for that, I'm going to divide it by 15. And when I'm done, I get that this thing is 829.7 miles. Yes, miles. All right. And so that's how you would use arc length. You can do some algebra if you were trying to figure out the radius of the circle or the radius of the Earth. And that's actually a pretty interesting thing. I'll add to the playlist a video that talks about how the ancients did this without cool things like Google Maps. Yes, they calculated the radius of the Earth. All right, that's all there is on arc length. We'll see you in class.